Hey, good morning, everyone. My name is Dongbo Wang. I'm a developer from PowerShell team and also a maintainer of the PowerShell repository on GitHub. I've been working on PowerShell for 7 years, but this is my first time standing on the stage of a conference and give a talk about it. So please bear with me. So this talk is about the design and implementation of some key components of the PowerShell engine. We will look at each of those components by inspecting and walking through the execution process of a simple script. So here's a diagram. This diagram is an overview of what happens when you are running a simple script from PowerShell console. The script is trivial. We assign a string value to $path and then run $path. Well, we don't have to worry about the details yet. We're going to walk through it step by step. So after pressing enter, this is what happens in the console host. The host will read the user input from the console, then create a pipeline, create a pipeline object with 2 commands. The first command is the input string. The second command is out default. The out default is a secret command that's in PowerShell. Whenever we run anything from the PowerShell console, this out default will be appended to the end of the pipeline. It takes input from the pipeline, including results or possible error records produced from the user input script, and render them onto the console in some predefined format. So it works closely with the formatting system in PowerShell. Finally, the console host will call invoke on this pipeline to start a new thread. We call that new thread the pipeline execution thread, which will resolve the command, the test commands here, into a command processors and create a pipeline and run them all. So the question comes up, what is a command processor? A command processor is where a command executes in PowerShell. So there are 3 of them in PowerShell. The first one, the name is a command processor. Well, the name is a little too general, but in fact, the first type only handles the C# commanderlet and advanced functions. Advanced functions are also known as the script commanderlet. They are essentially functions and scripts declared with the commander binding attribute or parameter attributes. So this set of commands, the C# commanderlet and advanced functions, they have common parameter support from the runtime. So like the parameters -verbals, warning actions, and etc. They have full access to all the PowerShell parameter binding features, including the parameter sets, the dynamic parameters, pipeline parameters, and etc. and etc. You may wonder that, okay, one of them is in C#, it's in IO binaries, and the other is in script. So how come these 2 can be put in the same bucket? Well, it turns out internally, the advanced functions are represented by a special C# commandlet called PS script commandlet. As you can see from the screenshot here, it's an internal type. It derives from the PS commandlet type, which is same as any regular C# commandlets. So that's also why we are calling this advanced functions a script commandlet, because internally they are commandlets. The second one is a script command processor. It handles simple script. Basically are the functions and scripts without the parameter binding attributes or parameter attributes. These sets of commands do not have a common parameter support, and the restricted parameter binding rules are applied to them. For example, you cannot use dynamic parameters with these commands. The last one is native command processor. It handles native executables. So in order to execute a command, 4 key methods are implemented by every command processors. They are do prepare, do begin, do execute, and do complete. They basically represent the life cycle of a command execution. Do prepare will run only once before do begin. It will set up some context information and do parameter bindings. While for native command processor, it also starts executable process, redirect the standard input, output, error strings as needed. The do begin will be called only once before do execute, allowing the command to initialize itself. For the command processor, it's going to run the begin processing method on the underlying commandlet. For the script command processor, it's going to run the begin block. For the native command processor, well, it has already been set up in the do prepared phase, so it does nothing here. Do execute. This method runs 0 or multiple times, depending on its position in the pipeline, and whether there are any pipeline input. So if it's the first command in the pipeline, then do execute will be called at least once. If it's in the middle of the pipeline, then it's totally driven by the pipeline input. If there's no input, like if no objects is written to the pipeline, then do execute may never be called. For a command processor, it's gonna do pipeline parameter binding in the do execute, and then run process record of the underlying commandlet. For the script command processor, it will, well, sorry. For the script command processor, it will read the input, bind it to the $underbar, and then run the process record, process block. For native command processor, it basically feeds the pipeline input to the redirected input stream of the executable process. Do complete. Do complete will be called only once after do execute, allowing the command to wrap up its execution. For the command processor, you're going to call the end processing on underlying commandlet. For the script command processor, you're going to call end block. For the native command processor, it will wait for the executable process to exit and do some cleanup work. So now we have a basic idea about what is the command processors, what they are, what they do. So it's time to say how do we resolve a command into a command processor. Back into the console host, the commands in the pipeline object are in the form of a text. So it's either a string of the script read from the console, or it's a command name. In the pipeline execution thread, we have to resolve the text commands into its corresponding command processors. For the string of the script, if it's a string of script read from the console, then parser will kick in and parse the text into an abstract syntax tree, which will be used to create a script block. And then a script command processor will be constructed with a script block. So it's a little it's straightforward for the script command processor in this case. But if the command is a command name, if the command is just a name of command, if the text is just a name of command, then things are a little complex. The command discovery component will kick in to resolve the command. So command discovery is a component where PowerShell search for a command based on a given name. The search algorithm looks roughly like this. First, the pre-lookup event handler will be triggered if it's set. So you can find the event handler in this place, $execution context, invoke command, pre-command lookup action. In this handler, you can decide which command you want to return as a result and tell the search to stop. If the search is not stopped, then PowerShell will look up the command to the scope chain. PowerShell is dynamic scoping, so all the functions, alias, commandlets, variables are all stored in scopes. In this step, the search will start from the immediate scope, then the parent scope, and so on until we reach the global scope. The preference order for the command types in the search process is alias, function, commandlet, PS1 files, and application, which means that it will search for alias first, and then command, and then commandlet, and then script files, and then application. If the command is not found during the last step, the module discovery will be triggered to look for the command from modules available in the module path. This involves module analysis to get the exported commands from all available modules. PowerShell tries to lightweight that there are two ways to do module analysis. PowerShell tries to use a lightweight analysis first. Basically, it's reading metadata from the module manifest to find exported module members, or parsing the script and analyze the AST to find exported members. If it has to, it's going to fall back to the heavyweight heavyweight module analysis by calling this import module -list available, which essentially go through all the process of importing the module, but without actually loading this element. The lightweight module analysis is usually sufficient in most of the common scenarios. The module analysis produces a table of commands exported from the available modules. The result is cached in the PowerShell process, so the same modules don't need to be analyzed again when there's another command search, like command discovery search. Furthermore, PowerShell will attempt to serialize the cache to a file so that other PowerShell processes can also benefit from it. PowerShell tries to make this deserialization as simple and efficient as possible. A serialization request is triggered when there's any update to this cache. However, the writing operations are held back until the cache becomes relatively stable, which means there are less frequent changes to the cache. Writing to the file happens in a task in a completely asynchronous way. Instead of using mutex to guard the file read-write access, PowerShell read-write the files completely depending on the file log, which means like if it's able to open the file, great. We're going to read the content. We're going to benefit from the analyzed results, or write the update cache into the file so that other process can benefit from it. If it's not able to read from the file, say it's being used by another PowerShell process, then for the reading operation, it will try 2 more times with 25 milliseconds interval, because if it's possible, we really want to skip the module analysis step, just use the already existing cache result. But it will give up after 2 more tries and turn to the module analysis by itself. For the writing operation, if it cannot open the file, it will just skip the write, because an update to the cache will always trigger another serialization request, so we can always write at a later time. After the whole process of module discovery, we will get back a table of commands exported from all available modules. If we find the target commands from the table, awesome. Then we're going to auto-load this module and return the result. If no command found, then we just have to give up. So if the command is found, then there's another event handler, post lookup event handler. It will be triggered if it's set. The font commandlets will be passed into this handler, so you can change which command you want to return by setting this command property of the event arg. By changing that, the search process will respect your choice and return the one you set in its property. If the command is not found, then the command not found event handler will be triggered if it's set. Again, you can decide which command to return as a result in this event handler. If the command discovery process was successful, then we will get back a command info object representing the command we are going to execute. Based on the command type of the command info object, the appropriate command processor will be created with the command info object. So for example, like as we can see here, it's a pseudocode. So if it's an application, we're going to return a native command processor. If it's a commandlet, we're going to return a command processor. If it's a function script, but it's using the command binding attributes, then we're going to still use the command processor. And other cases, we're going to use a script command processor. Okay, now that both commands has been resolved, so a pipeline processor will be created to chain them together and start the execution. Pipes are weird commands, like when the pipeline processor will chain them together, you're going to use the pipes like to aggregate the results produced from commands. Pipes are basically where commands processor writes out streams to, such as the output stream, error stream, warnings, and etc. When adding a command processor to the pipeline processor, the command processor will actually be set as a downstream command of the previous command processor's output pipe. So, for example, in our case, in this example, our default will be set as a downstream command in the script command processor's output pipe. And when a script runs and produces any results, the result object will be added to its output pipe, which will trigger a call to the doExecute message on the downstream command processor. The doExecute message will then read the object from the pipe, do parameter binding, do the pipeline parameter bindings, and eventually call the process record of the underlying commandlet, which is our default command in our case. Well, this is how two or multiple commands are chained together in the pipeline. And this is also how the output from one command flows to the next and triggers execution. And this is why we're saying that the doExecute message is driven by the pipeline input. Because if there's nothing written to the pipe, then the doExecute message of the downstream command will never be executed. Now let's back up a little bit and see how pipeline processors start execution. Oops, sorry. So the pipeline processor has a message, synchronous execute enumerable. And this message is the one going to start execution of a pipeline processor. It first calls doPrepare on every command processor in the pipeline to have them setting up context information, binding parameters, and do some extra stuff. For example, in native command processor case, it will also start the executable process, redirect input, output, error streams as needed. Then it calls doBegin on every command processor to allow them to initialize. Next, you're going to call the doExecute on the first command processor, and if that method produces any output, great. That will drive the doExecute message from the downstream commands to run. If it doesn't produce anything, it's fine. It just means that the doExecute message from downstream command may never run. At last, it will call doComplete on every command processor, which will wrap up the execution. Be noted that the output may also be produced from doBegin. When running a begin block or begin process method, it's very common that you're going to write out something to the pipe. In that case, the doExecute method of the downstream commands will also be triggered. However, by that time, the begin block or the begin processing method of the downstream command hasn't been run yet. So which is going to be a problem, which means they are not initialized. The solution to that problem is to call doBegin in a doExecute if the doBegin method has never been run yet. Similarly, output may be produced from doComplete, which will also trigger the doExecute message of the downstream command processor. But by that time, the doBegin has been called on all command processors, so it's going to be okay. So our script here, like the script we're about to run, it only has an in block. So its execution starts when doComplete is called on it. Now let's explore how a script gets to run behind the scenes. In order to execute the script block, it needs to be compiled first. Given an abstract syntax tree, the PowerShell compiler will visit every node and generate code for it. The generated code is represented in a linked expression tree. So for our simple script here, the generated expression block will be something like this. So you're going to call the static method set variable value and set the value to this variable $pass. And then you're going to call invoke pipeline, which will basically create another pipeline processor with a single command processor, dir, the get child item, and start execution with that pipeline processor. The compiler leverages dynamic language runtime heavily in the code. It used the dynamic expression plus call side binders to handle most of the dynamic bindings, such as member access, method invocation, indexing, binary operations, and etc. in PowerShell. Every call side binder has a fallback message, and that's where the dynamic binding happens. Take the PS get member binder as an instance. Well, this binder is used when you do any property access or member access in PowerShell. It has a method named fallback get member, which is responsible for generating the real code for the property access operation like $file.name. Let's look at the $file.name. For such a member expression in AST, compiler will generate the code roughly like this. Okay, it's going to get the value of $file. It's going to get a static binary instance based on the member name and whether it's an instance member or not. And then it's going to return dynamic expression with a binder and the target. It's worth mentioning here that a binder for the particular binding operation is static and shared across the PowerShell process. So if you need to do the same binding operation, the same binder will actually be used. When dynamic expression gets to run, it returns the dynamic expression. And when dynamic expression gets to run, it will ask the binder, hey buddy, what am I supposed to do? Because the dynamic expression doesn't know anything about late binding. The binder is taking care of the late binding. So the dynamic expression will just turn to the binder and say, buddy, what am I supposed to do here? And the binder will then call its fallback get member message with the value of a $file, do the late binding logic, and then return an expression and say that, okay, here's the real code, just run it. So you can see that the call side binder provides us a clean way to organize the dynamic binding code. And furthermore, it also makes the late binding much faster thanks to its binding result catching. A call side binder is able to catch 128 binding results. When a fallback message produces an expression representing a real code to run, it actually also produces the restriction for using that expression, usually based on the types of the argument passed to the fallback message. So the restriction and expression will then be inserted into the binder's cache, just like key-value pairs. Say later, there comes another member access operation, say $another file.name, and we assume the $another file has a value of the same type as a $file. In that case, this PS-get member binder will not call its fallback method again, but instead, you're going to find a match in the binding cache and return that corresponding expression immediately. So this avoids duplicate binding resolutions for operations for operations of the same category, and therefore it makes the script run much, much faster. Now we have an expression tree representing the operations in the end block. We have an expression tree representing the operations in the end block of the script. But as expression tree is just data. It's code as data. So how do we run it? The answer is to run turn the expression tree into delegate of executable code. Let's see what we have on hand. We have an expression block representing the actions we want to take for this end block of the script. And we have this some context environment where we can perform the actions on. So the runtime environment we have here, like it's represented PowerShell by this type function context, including things like the script block is being compiled, it's being compiled here. The execution context that refers to other components in the run space, the pipes where the streams are going to be written to, and so on and so forth. So it's natural that, okay, we have actions to perform, we have the environment to perform the actions on, so we have an expression, we have Lambda expression here, which represents the actions to perform based on a context parameter. Now, okay, now we have a Lambda expression that represents a delegate for the end block of the script, but it's a still expression. So how are we going to run that expression? It's a delegate expression, but it's still data, so how do we run that? Of course, we have to generate a real delegate with the executable code from the expression. There are two approaches to do that. The first one is to compile the expression tree into IL directly by calling this compile. There's a .NET message on any Lambda expression instance named compile. When you invoke that, it's going to compile this Lambda expression into IL directly, and will produce a delegate pointing to the IL code. So this approach can generate a very fast executable code, but compilation to IL is very expensive, which means it's very expensive to generate a delegate in the first place. The second one is to run with the interpreter. PowerShell uses the same interpreter as in link expression in .NET. The code was copied to PowerShell in version 3 with some PowerShell specific changes. There have, since version 3, we have some bug fixes to the interpreter, but we haven't synced the code with the .NET. So the code base between the PowerShell code, the code base of this interpreter between PowerShell and the .NET might diverge now. Given a Lambda expression, the interpreter will visit every expression node in its body and emit instructions. Every instruction has a run message, which contains a real C# code that will execute when the instruction runs. Well, the instructions works in a way as if they are on the single stack evaluator. So they can read data from the stack, they can remove data from the stack, they can push data onto the stack, they can call message, they can copy variables to the stack and from the stack. Here's an example of the run message from the new array bounds instruction, which will create an array actually. So we can look at the code here. It's just a C# code. The frame.pop is going to pop a data from this stack, and frame.push will push the data back to the stack. So what it does here is it's going to get the rank value from the stack and create an array, and then push the array back to the stack. After all instructions are generated, the interpreter will create a delegate, which essentially points to an instance message of the interpreter. That message will create a stack and execute the instructions one by one when it's being invoked. This approach, this approach to turn expression into delegate generates less efficient executable code because it's just C# code. It's not IL. And but the benefit from that is that it's less expensive to generate delegate in the first place because it's actually only creating a delegate pointing to an existing function, which is an instance message within the interpreter instance. PowerShell takes advantage of both approaches, actually, when running the Lambda expression. By default, PowerShell will run the Lambda expression with an interpreter. This is because usually it's too expensive to generate the Lambda expression into IL. And even though you're going to produce much efficient code, it takes too long to generate delegate in the first place, so it will become useless. However, we do want more efficient code, more efficient executable code for hard script that runs many, many times. So PowerShell introduces a threshold. When a script is not too large, like when a script is not too large, say it contains less than 300 statements within the script block, and the interpreter-based delegate runs more than 32 times, then PowerShell will believe that, okay, this is a hot script and runs many times, and it probably worth to compile the Lambda expression into IL directly to generate a more efficient executable code. And in that case, PowerShell will do this compilation in the background. And after the delegate is generated, it's going to switch the pointer to delegates and start to use the IL delegate for subsequent executions. There's another place in PowerShell interpreter which is going to do the similar thing, which is the loop instruction. So let's say the script block itself doesn't run that many times, but a loop in the script block runs many, many times. In that case, PowerShell will do a similar thing, like it's going to try to compile the expression of the loop into IL code in the background thread. And then once it's complete, it's going to switch the pointer and start to use the IL delegate for the loop instruction. So by now we're going to have a delegate with executable code, generated for the end block of the script. The delegate will be invoked to perform the operations defined in the script, and also the delegate will be saved into the script block that's being compiled. So the next time you run the same script block, you're going to directly use the delegate instead of compiling it again. Of course, the execution of script will generate the output, files, directories, which will be written to the output pipe and drive the downstream command to execute, which in our case, the downstream command is going to be the out default. When there's any input, any results written to the pipe, the process record, the process record method of the out default of the downstream command out default will be triggered, and it's going to render the output onto the console based on the predefined formatting. So now we're done with this script execution. This is a whole process. We can look at it again. We get a script from the console. So anything you type onto the console, once you type enter, special commandlet, out default, will be appended to the end of the pipeline. So actually, we're going to generate a pipeline processor with two commands in it. The first one is a script you type into the console. The second one is out default. We have to resolve the text form of the command into its actual command processor. For the text, for the string of text we received, the PowerShell received from console, it's sort of easy that we're gonna parse the text, generate an AST, and construct a script block from the AST, and then construct a script command processor using a script block. For a command name, it's relatively complex. We have to go through the command discovery process. We have to search the scopes. If we cannot find anything, we have to trigger the module analysis. And if we still cannot find anything, then the command not found even handler will kick in, and if you set it, it's gonna help you to resolve the command. Okay, so after command discovery, let's say we resolve the command, then we're gonna have two command processors resolved. We're gonna create a pipeline processor to chain them together with pipes. And the command processor will be started when you are calling this synchronous execute enumerate method on it. You're gonna call this do prepare message on each of the command. You're gonna call do begin message on each of the command. for the first command in the pipeline, you're going to call do execute, which if produce any output, going to drive the do execute message from the downstream commands. And then in the end, and call do complete on each of the command processor to wrap up the execution. In our case, the simple script does not have a begin process, does not have a begin block, does not have a process block, only has an end block. So the execution of this script command processor happens when the do complete is invoked on the script command processor. And then this is what happens when you're running the script. We're going to have the partial compiler kicks in, consume the ASD tree, generate an expression tree, which in our case, like for this simple example, the expression block going to be relatively simple. They're going to set the value to $pass, and then construct another pipeline processor with a single command processor, which is dir, and run it. And now we have the command, we have the expression tree, like we have the expression representation of the code we want to run. So next step is to turn the expression into real executable code, which means we're going to generate a delegate from the expression tree. And the expression tree we have here is the action we want to perform, and then we have another thing, which is the environment context, which we want to perform the action on. The environment includes the script block that is being compiled here, the execution context, which refers to other components in the run space, like provider, for example, eventing, and modules, like many other things. And also the pipes, because, see, we are running from the script command processor, so pipes are important here. So we have the action, we have the environment to perform the action, then we combine them together, we have a Lambda expression representing the delegates of the end block of our script. So next step, generate the actual executable code from the Lambda expression. There are two ways of them. One is to directly call the compile message on the Lambda expression, which will generate an IL code, return a delegate, point to the IL code. Well, the code is very efficient. The code generated is very efficient in this way. However, it's too expensive to generate delegates in the first place, so we cannot always rely on that. The second way is to run a Lambda expression with the interpreter, which basically gonna visit every node in the expression body, generate instructions for them. And then we have an instance message with the interpreter, which gonna create a step and run instructions on a step one by one. So the code generated from this way, from the interpreter, it's like less efficient compared to the IL. However, the delegate is very fast to be created because it's actually just a delegate point to an existing message within the interpreter instance. Therefore, PowerShell depends on the interpreter by default. However, PowerShell can also take advantage of the IL code. And the way to do that is to define a threshold. The threshold is used to determine whether a script is a hot script, means that the script is going to be run many, many times. The default threshold number is 32 times, which means, okay, I'm going to run it with the interpreter, and if the script block gets run for more than 32 times, I believe that it's a hot script, and I assume that it's going to be running for even more times. In that case, PowerShell will start up a background job, like going to try to compile this Lambda expression on a background thread. And once that is done, you're going to switch the pointer of the delegate and start to use the IL delegate for subsequent executions. A similar thing is going to happen for loops in PowerShell. So, for example, the script itself will only run once. However, it has a loop that runs many, many, many times. In this case, PowerShell will detect that, okay, this loop has run for more than 32 times. And then it's going to start the background thread, try to generate the IL code for the loop. Once that is done, again, switch the pointer. And from then on, when you're running the loop instruction, you're going to run the IL code instead of the C# code in the instructions. So after this step, the compiler basically generates a real delegate representing the executable code for the in block of this simple script. The next thing is to call the delegate to run the operations defined in the script. And after doing that, it will also save this save the delegate into the script block, which means if you are running this script block again in the future, you don't have to compile it again. You can just use the delegate to run it. So that's the execution of the script command processor, so which will produce some output, which will be written into the output pipe and drive the do execute method of the downstream command, which is our default in this case. And our default will receive the result and render it onto the console in a predefined format. So that's the whole process. Yep.
How is that handled if for instance, if I type dir on the command line for 32 times, would that trigger the...
No, it's not the same command, it's not the same script block anymore.
Okay.
Every time you type something on the console, you tap enter, it will be parsed into AST tree, and the AST will be used to generate a script block. Okay. So that's a script block.
As soon as I do a loop or something, it would trigger...
Yeah, if you are typing like something, for example, you type something and have a loop in it, and the loop is going to run many times, then we're going to consider that to be, a hot pass. However, it's not like PowerShell going to generate an IL for any loop. It has some restrictions because it might be too slow. We only consider generating IL codes for a loop if it's contain less than 300 statements. If it's more than 300 statements in the loop, we consider it too big. So it's going to be too expensive to generate an IL code for it, which means that we're going to continue to depend on the interpreter to run it.
I have one question to that too. What if a script runs only once, but it runs every single day? So can I save it or compile it to file?
Well, in that case, it just have to be parsed again into a script block and compiled again, because it's unless you are importing it as a module and the module stays in the same process and you are using the same PowerShell process to run it every day. In that case, they're going to reuse the same script block.
The other way to say that is this is a hotspot compiler.
Is there a way that you can set a flag that you can mark your script block as hot and make it be compiled in the first round?
Sorry, can I say that again? I'm sorry.
Can you mark a script block as hot so it will be complied?
You can't.
Can you manipulate the threshold?
You can't. It's something fixed in PowerShell code.
Okay.
You don't have to mark it as hot. If it's really hot, if you're running many times, PowerShell will detect that and will do the IL generation in the background thread. Which means if you have a loop which runs many times, PowerShell will detect that.
Okay, but that means that a loop that runs 35 times will be somewhat slower because at the 33rd time,
well, if the first three, the threshold, the default value for threshold is 32, yes. Which means the first 32 times, or maybe even more, because by the time you reach 32, PowerShell will start to do this IL compilation in the background thread, which means you're probably still going to rely on the interpreter for the next few runs. But after the compilation is done, you're going to switch the pointer, start using the IL generator, which means that maybe the first 32, 33 times of the execution will become relatively slow. And after that, the IL delegate kick in, and it's going to be faster.
And that's kind of the reason why measuring your performance is slow in the beginning, but it gets faster as the more often you press F5?
I'm not sure about that. I think, Bruce.
If you look at the surprise. Yeah, well, Jason has an example of the burn console script that displays a fire on the screen, and if you run that post V3, you'll see that it's slow at the beginning, and then just all of a sudden it speeds way up, right? So you will get variable performance based on how often you're executing stuff.
Yeah, I guess that also depends on how large, how expensive to run your script in the first place with the interpreter.
Yeah, we also noted two strange things. Maybe you can explain them. If you have a pipeline compared to if you create, like a pipeline with the for each, compared to a function, the function is much faster. So has that to do with compiling in some way? Oh.
No, the problem there is basically that the pipeline processor is really slow. And a lot of the optimizations that Dongbo has been talking about could be applied to the pipeline processor. We haven't done that yet. If there's anybody interested in doing that, let us know.
Yeah, I want to add one thing to that, which is like we're using a loop in a script block. The loop will be like, if we're running 32 times, it will be count and say that, okay, so how fast it's going to be compiled to IL. But if you're using a for each, it's not a loop, which means it will not be count. So it's always going to be running using the interpreter probably.
I just want to say that hopefully we're recording this session, because what Dongbo has done here is absolutely phenomenal. He has expressed some of the most complex portions of PowerShell in the most incredibly efficient way. I mean, the point is that if a lot of these things you got to like understand, like working this for a long time, I was able to follow everything that he said, and it was incredibly efficient. There's like very few tangents, etc. So this is a talk you'll want to watch again and again to like understand what he said, but it's incredibly efficient in this discussion. And certainly if you've wanted to take a look at the PowerShell code, right, it's now all open. This would be the first thing you want to do, is to watch this talk a couple times and then drill into the code, and your eyes will be open.
Yeah. So I want to like mention it again, like say it again. Because when I started to look at the PowerShell code, it's always confusing to me what the compiler does actually. So I know that PowerShell is going to generate AST representing the structure of the script, and then pass it to the compiler, and then it suddenly starts to run. So it's really puzzled to me in the very beginning that what the compiler does behind the scene. So I think it's okay. Like I think it's okay to summarize it to a very simple sentence that the whole purpose of the compiler is to generate the Lambda expression representing the operations you want to do with your script block. And then in order to run this Lambda expression, you need to rely on the interpreter to generate a real delegate pointing to the executable code. So the whole thing compiler does is to, okay, take the AST tree and then finally generate a delegate with executable code. But, definitely the interpreter was involved in the process, but it's still within the compiler. And outside the compiler, what you see is that it takes the AST, it generates the delegate with the real executable code. So I think if you have that in mind when looking at the code in the compiler, it's going to be much easier. And now it's a summary. So we inspected the execution process of a script block from the PowerShell console, a script from the PowerShell console. We walked through the process step by step. It's not everything. Like I didn't touch the providers, which they're gonna gonna depends on. I didn't touch the formatting system, which all default can actually depends on to do the rendering. I didn't touch many other things, but these are the basic key components which are involved in the execution of the command of the script. So the components discussed here are command processor, command discovery process, including the module discovery and auto loading, and how do we cache the module analysis results back to the disk, and how do we consume it or benefit from the file as well. And the pipeline processor, like how it's chain the command together using pipes, how it's start execution by calling do prepare, do begin, do process, do execute, and do complete. We talked about the compiler, how it's consumed the AST, generates the expression block representing the actions, and then combined with the environment context to form a Lambda expression. And then we talked about interpreter, which a compiler uses to turn the Lambda expression into a real executable code. So this is the whole process of running a simple script from the PowerShell console. Think that's it. Any more questions?
I'll come to you, so we have it on the recording. There was one here first.
Is there a way to see the Lambda expressions from the compiler?
Sorry, where to see what?
Is there a way to see the Lambda expressions that the compiler generates?
Well, you have to use a debugger to see it. It's open source, so you can always set a debug, like breakpoint in the code, and see the actual Lambda expression kind of produced.
I wanted to ask if there is any performance difference running an advanced function and a normal function, because different processors are used for them.
Yes, different command processors are used, but actually even if you are using an advanced function, when you are running anything in a function, it's still going through the same process here, because it's a script essentially. However, it's represented in a different way. So there's no performance difference when you're running them. It's just some other restrictions, especially the parameter binding. Like, you know that it's very restricted for the simple functions to do parameter binding.
Why is it that dot source code is faster than not dot source code?
Sorry?
Why is it that when you call a code dot source, that it is faster than if you don't dot source it?
It's faster than dot source
There was
it?
a discussion on that. Maybe it's fixed now in 5, but it used to be that way half a year ago.
I think, yeah, you too. Yeah.
The only thing that I can think of is it's not creating a new scope. Right? It saves away the magical variables and then executes in the current scope. And scope creation is fairly expensive.
I think that depends actually.
Actually, it was the other way around. So if you create a scope, it was faster. That's a funny thing. Yeah, if you dot source it, then it has its own scope, right? Oh, so then it was the other way around. So okay, then it was slower with dot sourcing. But I'll try out. I don't want to blame. I want to embarrass myself. So
I think I can answer your question here. Like when I'm talking about the compiler here, I skipped a very important thing actually, which is a very detail oriented. It's a variable analysis. Which means that if we are running a script block which is going to create a local scope, PowerShell will do the variable analysis and figure out what variables in your script is able to be cached locally, which means not actually stored in a scope, but using a tuple array, or actually it's a tuple array, something like that. You're going to store a variable in the tuple array by using index. So it's not actually saving the PS variable into the scope, but actually just save the data in a slot in the array. So it makes the variable discovery, variable value retrieval much, much faster. So usually, when you are running with a local scope created, it's faster than dot source it.
okay, I'll try to sort of get an example done, because we stumbled across it when we used measure command, which is not using a different scope. And then when we use different scopes, it was much faster, but we'll try.
Yeah.
Hi, can you elaborate a little bit more how the pipeline is working when it has to process, for example, a lot of data by using several commands, and it is streaming the input from the first command to the next command? Is it using multiple threads to work on the data more efficiently?
Yeah, is that, you mean strings, or?
Yep.
Are you talking about the pipes between the commands?
Is the pipeline single-threaded?
Yes, it is. In PowerShell, a pipeline execution thread is single-threaded, which means every run space has its own default thread to do all the actions.
I'm getting my sports workout this morning.
Yeah, to elaborate on that a little bit, so one of the core design decisions of PowerShell stemmed from the fact that .NET, unlike Java, is not thread safe. Okay, so what that means is that if you're going to use multiple threads, the caller is responsible for the concurrency control. Okay, now that allowed .NET to be very fast compared to some Java implementations, but it means that the programmer, whoever calls the .NET class, is responsible for the concurrency control. In PowerShell, the caller is you. Okay, now most professional developers who've been doing this 20, 30 years screw up concurrency control. So the fact is that, you know, the general admin community would never be successful in that, in trying to accomplish that, because concurrency control is one of the hardest problems there is. So that's why, you know, PowerShell is essentially single-threaded. You know, conceptually, your scripts are single-threaded. Now, additionally, there is no, unlike Windows, when you have a pipeline, you have multiple concurrent processes talking to one another. In fact, the better way to think about PowerShell is that you have this pipeline syntax, but in fact what we do is underneath the covers is we set up this directed acyclic graph with a data flow engine, which is to say that when you type A, pipe to B, pipe to C, by the time you're executing C, you can walk up the stack and see B and A. So they're actually on the stack. So that's a different way to think through. It's a very different implementation.
That's all right. In the back, of course. You're sort of controlling this. The next one is up there.
5 minutes, okay.
I'm still a bit stuck on the loop and the 32 iterations.
Okay.
Would it be in any form advantageous to have if you have a very heavy loop with a low iteration count, to fake the first 32 and then start the real loop? It would be a bit dirty, but would it be quicker?
I think probably first 32 might work. I don't know about that. I never tried. But I guess the general guideline should be just trust the PowerShell. That's the right thing.
You also mentioned that you do not do this IL compilation for each. Does that mean I should stop using for each? If I'm doing
no,
heavy lifting, or
it's for different purpose. Like I think Bruce might have a better opinion on this, but in my opinion, it's for different purpose. Like for each, it's some simple processing you want to do through a pipeline. If it's a loop, it might be some heavy work you want to do. So yeah, so for each is not count as a loop instruction. So it's yeah.
I just tend to use it a lot because it's
Yeah.
easy.
The for each object. It's a command line for each dash object. It's not a for each statement. It's a for each object we're talking about.
So any other questions?
Oh, sorry. Is that?
I would like to postpone because it is already time.
Oh,
Thanks
yeah,
so
sorry.
much for being here. I think this session was really
Thank
good.
you.
Yeah. Thank you so much.